Okay, hi. Good afternoon, Kalispera. I've been researching for years ontologies, collaborative knowledge platforms, topic map, associative data model, and associative technology products like ClickView, for example. That is so interesting to share with you, but I'm afraid time is not permitting to do so. Eventually, I was convinced that it is worth developing a database framework that is based on that technology. So now let's find out quickly what is your background and experience in database market. How many of you have worked with relational databases? 2, 3, 4, 5, 6, 7, 8. Okay, how many of you, most of you actually, how many of you are familiar with graph databases? Property graph, triple stalls, so. Okay, same response almost. And how many of you have worked with ClickView or click-related technology, or simply know about it? 2, 3, 4. Okay, now these are far less people. Okay, that's great, thank you. Now, this is an overview of what is coming next. I will talk a bit about which part of the big data problem we're attacking with our technology. Then introduce our database framework, make a demo to explain the key differentiating factors, discuss how connected data London meets our objectives, and finally unfold to you our future plan. Let's begin. Different aspects of the big data problem are often highlighted with a series of V's, keyword topics. Those most appropriate to describe the soft launch of our product are velocity, validity, variety, and variability. We have designed and implemented a middle layer between the technical users and the end users. So apart from the ETL functionality, I noticed that most often what is ignored is the ability to enrich your data resources. And of course, it's the whole procedure of how you correlate, aggregate, and retrieve data. All these procedures do not have to do with the volume or even the velocity of big data. They are dependent on how you define and manage smart data. State-of-the-art DBMS are designed in such a way to cope with a multimodal data architecture. What is missing here is a multi-perspective database framework to pair with these systems. From a conceptual point of view, we are using entity, attribute, and association abstract concepts. Switching to a logical perspective, it can be viewed as a hypergraph. It will take me a long time and to go through each one of these perspectives. Instead of that, I would rather focus on those three that fully characterize our database framework and summarize it with three key terms: associative, multi-dimensional arrays in the core database engine, and associative entity that resembles the join table or of entity relationship data model. Semiotic by design and in theory based on R3DM, S3DM data modeling, and hypergraph in logic, where the first class constructs are a hyperedge that connects many hypernodes and represents entities or record tuples, a hypernode that is always connected to a hyperedge and represents an attribute or a set of values which we call hypercollection, and the hyperlink, which is a bidirectional edge that connects a tail node to a head node and represents a many-to-many relationship between entities or between entities and attributes. Okay, and now it's about time for our demo, and we have to bring this other screen and continue with my notes, because yeah, so we bring up now the traversal and hypergraph neighborhood. Yeah, this one. Thank you. Okay, a picture. A picture, where's the picture? Let's go find the picture. Okay, no problem. That's where the picture is. A picture, they say, worth 1,000 words. That is why we start our demo with an illustration of a hypergraph neighborhood. What you see here are two rows from a table that represents parts. So a red Acme widget washer that has an ID of 1993 and a weight of 142.88 kg, that's the unit, and a silver Acme widget washer that has an ID of 1994 and a weight of 142.88 kb. Obviously, there is a cleansing problem here for those that have been dealing with cleansing cases, okay? And you see how they are differently related, kg, kb, but with the same label, okay? The same name of... the green nodes are the hyper edges, and the red nodes are the hypernodes. Because we deal with instances of the part type and values from its attributes, we are using the alternative terms hyperbond and hyperatoms. A key difference from other types of graphs is that the label of the edge that we call hyperlink is not needed in order to traverse the graph or perform queries on the system, and we will explain why now. We start by selecting a hyperatom with a string Acme. This is actually further, is it here? Yeah. Just, where is it? I'm not sure where is this, that is. Maybe there's the next slide. It could be further up. Get hyperatoms. Yeah, here it is. Okay, I found it. So, as I said, we start by selecting hyperatom with a string Acme. The dictionary of our framework returns two hyperatoms. Okay, you see them here and here. Each one has an ID key and a reference key to the value. Each hyperatom is connected to at least one hyperbond. The one we selected has two hyperbonds there. And from those two hyperbonds, we get all their connected hyperatoms. And that is how we find what is in the neighborhood. You see, get part hyperbonds, get part hyperatom sets, all this stuff. And we don't use the label of the edges to traverse the graph. Why? Because we dereference the key addresses of each node. It's as you see there. And that is also evident from the fact that we can have any set of labels to describe the edges and or direction of traversal. Okay. We see that in the next graph. Where we have drawn hyperlinks in both directions. Now let's bring the next graph now. I think is get cassette read B. Is that changed now? Was it no? Yes. Okay. So in this demo, all of these are running live in a system that is online, and I will be very happy to go through that at the end of the day and demonstrate it live. For those of you that are interested in looking how it works, and here is the via and the node via class, the object that links the two nodes, and as you see here, the different labels, you see them at this point, okay? I can give any set of labels for the direction that goes forward and backward, for forward and reverse. So it doesn't matter really what labels you are gonna set to your system. You may conceive that more easily if you think about these labels as roles. Querying our system is always a matter of what kind of filtering you apply. Another major difference from other systems is that you never write down queries, but you change the parameters of functional commands like get something or add something. This is already being demonstrated to you with all these demo here. When I'm writing the commands, for example, where is it? Yeah, like this one, for example, for k in list, triad get what equal hyperedges from the system, from the concept, and you print the result. If we want to be more specific, so in our framework, it's not only entity tuples that you can filter. Actually, those here are filtering tuples. You see, for example, expand part hyperedges and expand catalog hyperedges. I'm asking the system, give me all the hyperedges of that concept, of that catalog thing, which is the con 30, and then it starts printing out the tuples, which has made from links, from the links that is on the hypergraph. The hyperlinks, you don't have already links. And so in our framework, it's not only entity tuples that you can filter. For example, in this demo here, I want to show you, in this demo here, you can filter collections. Collections are the domain of each attribute, the values it takes, okay? So you're asking what hypercollections from this model, which is the supplier part catalog, and then the system spits out all the attributes with the values for each thing. The only system I have seen, well, which pretty much doing the same is ClickView and another one. So filtering collections is an important operation for cleansing, and that's where you see here the part unit, for example, at this stage here, part unit LB, KG, KB, GR. So you're cleansing the KG and the KB units. KB has to become KG. What else? And then the last key difference from other graph databases that I want to demonstrate is the mapping of multiple data resources to a data model. This is pretty much important, very important. This is a fundamental part of our framework. Those of you familiar with the entity relationship model, let me bring this one in front, data model. Where is it? Okay. And then this is the model, the concept, supplier, catalog, part, okay? And that's how it can be also visualized like a hypergraph. And another visualization here comes at the end, I think. Everything in the system is a hypergraph, okay? Whether it is a model, whether it is data values that are connected, again, like the model. And those of you familiar with the entity relationship model are aware of the stage where you have to design a diagram with the tables, columns, and even data types for each column. It's pretty much the same here. You can define your own custom data model and specify the entity attributes and other characteristics. In the current implementation here, we load the model from a JSON file, and then we can add it to the Triad framework database and draw it as a hypergraph, which you've already seen. Now, finally, then once you have your model, then what you need is to add your resources. It's a similar kind of method, which you create a hypergraph from the data resources that you load on the system. But somehow, the data resources with the data model have to match the columns of the data resource with the attributes of the model. That's the important issue here. So how you map them, how you match them. In order to match them, you have to do what we call mapping. And the mapping is based on a bipartite matching, which I'm going to show you right now. The bipartite matching of two sets. Here we are. The column set, okay, on the left, and the attribute set on the right. And these two sets have now to match, which pretty much which means to provide the matching pairs, provide the matching pairs between those two. And once you provide the matching pairs, which are those things here in the list, here what you get. And that is saved in the system, and you have your mapping. Now the system knows how to get the values from the data resource and put them in the model, and finally place them in collections in data values, okay? And then you do the same for the entities. You map also the entities with the tables. That's the mapping. And then that's what is written on the system. This is what is written on the system. Everything has an ID as we know, as I've been explaining. And the column, the M key column says what is the model attribute that has been mapped this resource, and what's the name of the attribute or the entity, okay? And the M of M key is the collection, and so on and so on. So this is the mapping procedure. This concludes our demo. I'm offering to repeat it on a live system, as I said, at the close of the day. And at this point, we return back to continue our presentation, please. I think, I don't touch it anyway. I'm not a technology person. Okay, yeah. So we continue at, have to bring the slide 12. Demo add model. Where is it? Our objectives. Our objectives. Okay. Our objectives. The current implementation of our system is based on Intersystems cache DBMS for the back end and the associative semiotic hypergraph engine, while the front end that you saw, it is built on Python, Jupyter notebooks, and several classes that make a package that acts as an interface between the database and the Python console. Naturally, we want to promote our technology and framework to both Intersystems cache and Python developer communities. When we reach a maturity level, we are seeking to become a global distributor, and we will act as a bridge between vendors, their partners, and industry clients. That said, our future plan now, our future plan is to develop a go-to-market plan together with our partners and supporting vendors with a goal to build a self-service associative semiotic hypergraph BI system. I think everything has to reach, that's the utmost goal, how you reach the end user at the BI level. So what you saw here, it's a system for developers, but if we got the support, we get the support, we get the funding, we get the people, then we reach that stage, the stage of a BI. Our current product needs a lot of testing and further development, and we have extremely limited resources. We're just a couple of guys doing that. Should become open. My plan is to make it open and accessible to the general public, but solutions can be either proprietary or open source, or a mixture perhaps. And finally, we reached the end. That's our mantra there. We build powerful, meaningful relationships easily. Hope you've been convinced anyway. And I would like to thank my sponsor that covered the expenses of this trip. She's my wife. Thank you, darling. Thank you all for your attention. And questions, please.